So we're finding the missing side. Since these are right triangles, we can use Pythagorean theorem. You know, depending on different kinds of triangles, you would have to use different techniques. You can still find missing sides in triangles. That's usually actually one of the fun things that trig lets us do for any kind of triangles. It lets us find missing sides. But in a Pythagorean theorem question, in a right triangle question, we can use the standards of the Pythagorean theorem, or the basics of the Pythagorean theorem. Kind of get all that together, move that down there. And I was hoping that some of you would look at number 1 and go, oh, yeah, I know that one. If the hypotenuse is 5 and a leg is 4, do you remember what the other leg has to be? This is kind of one of our favorite right triangles. Yep, it's got to be a 3. That's that 3, 4, 5 special right triangle. That Pythagorean triple, a lot of teachers teach you. There's certain combinations that are fun to know and memorize, and then you don't have to always work it out. But if you don't remember that, there's no stress on that, because we set up Pythagorean theorem. And so x squared plus 16 equals 25. Move all this down. And so x squared, if we, well, actually, let me do this. If we subtract 16 from both sides, we get that x squared equals 9, which means, and this is where geometry and algebra kind of duke it out a little bit. If we're in algebra, x is plus or minus 3. Okay? The absolute value of x is 3, so x is plus or minus 3. But because of the context, this is kind of almost like, even though we don't use this when we talk about this, but it would be good if we did. Oh crap, I just forgot the name. Blah, 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 when we're doing logs. Extraneous, right? Technically, x equals plus or minus 3, but based on this kind of problem, negative 3 would be extraneous. X has to be 3. Okay. Algebra-wise, x could be positive or negative 3, but geometry-wise, x has to be 3. Everybody good with that? 6 squared plus x squared equals 9 squared. We're not going to get pretty answers for all of our right triangle problems. There's all kinds of right triangles that have not whole number sides. So we're not going to let that freak us out, even though we are going to talk about some of the ones that are super pretty a lot. Move this down here. Kind of block this off. Woo. So in this case, x squared is going to equal, if I subtract 36, and I don't mess up my subtraction, make some space here, okay. X squared is going to equal 45. So here comes my when I start having a conflict with myself. What kind of answer do I want? Well, as an applied calc teacher, if x squared equals 45, so x equals the square root of 45, that's a fine answer. Even honestly, as an AP calculus teacher, that's not a bad answer. We're very prejudiced against radicals that are not rationalized, but they're actually not that horrible of a thing. But if we wanted to make it a little bit more mathematically beautiful, I could rewrite it as 3 root 5. Now, I'll tell you something about me. I'm not going to mark square root of 45 wrong. Absolutely not. Because it's not wrong. It's right. The square root of 45 is perfect. As long as I subtracted right. As long as I'm not being dumb. No. Okay, I'm right. But 3 root 5 is a slightly nicer answer in the terms of mathematics. Okay. It's a more elegant answer. It's like using better vocabulary in your writing. And if you're going to be a calculus student, there would be a level of being able to make sure you can use nicer language if necessary. So root 45 is okay. 3 root 5 is a little better. And if you're sitting there going, well, how the heck did you do that? Maybe you forgot. Remember 45, if we rewrite it as 9 times 5, we can look at the square root of each factor, and the square root of 9 is 3. And so that's how root 45 becomes 3 root 5. Okay. Like I said, I'm not going to lose my nonsense. I'm not going to mark that wrong. No way am I going to mark that wrong because it's not wrong. But yeah, that's just a little bit prettier. So, do I like the 3 root 5 a little bit better? Yeah, I gotta admit it. I do. I'm a little snobby. I do like it a little better, but I'm absolutely not gonna mark it wrong because it's not wrong. All right. So, let's see. Number 3. Well, this one, easier. I gotta find the hypotenuse. 2 squared plus 3 squared equals x squared. That's 4, and that's 9. And so that's 13. And so nothing we can really do on this one. There's no snobby, nicer answer. Root 13 is actually the best answer you can give me. It's the, even though you're like, oh, I like that answer. It's the best answer. It's the most exact answer. And we're not using a calculator, so we're not going to get anything different than that. If you do practice problems for me with this and you give me decimals, I'm going to know you cheated because there's no way that you know what the square root of 13 is. Right? And decimal answers are what calculators will give you. Root-based answers are what you get when you don't use your calculator. All right, how many people are feeling pretty comfortable? Okay, tell you what, better, let me change the question. Scale 1 to 5. How comfortable, show me with your fingers. How comfortable are you with Pythagorean theorem? 5 is very comfortable. 1 is, yikes. Okay, yeah, I mean, yeah, we're pretty, yeah. You maybe don't love the arithmetic all the time, and you might be a little worried that I'm gonna like throw these ginormous numbers at you, but, which you shouldn't be worried about. Overall, it's just, can we find the missing side? Now, in geometry, there were 2 right triangles that were special. Let's talk about those 2 guys now. Special right triangles. And the reason that they're special is because their sides, while they fit the Pythagorean theorem, they also have like another nice relationship between them that's easy to figure out information about the sides of the triangle, and it's easy then to do some of the other things we're going to do with triangles and trig. Okay? The first one is this guy, where you've got a 90-degree angle and your other 2 angles are both 45 degrees, which makes both sides equal to each other. What's the name for this kind of triangle with 2 congruent sides? This is an isosceles triangle, right? So this is an isosceles right triangle. And some people might call it a 45, 45, 90 right triangle. A 45, 45, 90 triangle. Now, let's hit this with a little Pythagorean theorem for a second. If both my legs are equal, then if I call one leg x, I could call the other leg x. Okay. 4 and 4, 6 and 6, 9 and 9, whatever. X and x. And I'm going to just say, we'll call him C because we like to call him C. If I set up some Pythagorean theorem using those letters, my two legs would be the same, so I'll just call them both x. Instead of using A and B, I'll just use one common letter for both. So x and C in a right triangle would be x squared plus x squared equals c squared, which would mean that 2x squareds equals c squared. And if I'm looking to solve this for C, or have a way to talk about C, if 2x squared equals c squared, then the square root of 2x squared would equal c. That's me just taking the square root of both sides. And then, if I write that a little nicer way, a square root of 2 times just an x is what c would be. Now that was my very, very long way to kind of remind you or review with you the special combination of sides that you get in an isosceles right triangle. C, the hypotenuse, is always equal to whatever the leg value was times the square root of 2. How many of you vaguely remember talking about that? Yeah? Anywhere? No, okay, interesting. Maybe this didn't happen. This part may not have happened. Okay, that's fine. So, because the Pythagorean theorem has to work, and because you have an isosceles triangle, which means these two numbers are the same, whatever these numbers are, this C automatically is equal to the leg times the square root of 2. Now, at first you're like, that's annoying. Do I have to know that? Yeah, and other than being annoying, it's actually also kind of super duper helpful, because that means when we know something like that, when I go and do a problem like this, and I'm like, la, 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 and this is 6, and this is 6, and it says, okay, find C, I can do this a super quick way. I know C is going to equal that. I know that's going to happen. If I do the work, 6 squared plus 6 squared equals c squared. So 36 plus 36 equals c squared. 72 equals c squared. So the square root of 72 is c. I can get that pretty answer for c without even going through any of this work. Could you tell me c is equal to the square root of 72? Absolutely. Yes, you can. Okay. But the prettier version of the square root of 72, since 72 is 36 times 2, when we clean that up, that is 6 square root of 2. I love shortcuts. If I can take a shortcut, that's great. So I don't have to run a whole Pythagorean theorem application on this problem because I know this special relationship is always going to happen. Yeah? No? Sort of? The hard part about trig is there's a lot of memorizing. Okay? And I think that's where, you're like, trig isn't too bad, but when people talk about they don't like trig, you're like, here it comes, like, there's a lot of stuff you have to memorize. And some of this stuff you would have maybe gotten a little stronger, but unfortunately 2 years ago is when you were in geometry, and at the end of geometry, all hell broke loose. So special right triangles may have not been part of the discussion. Okay. So, how am I going to test you on something like this? Well, if I gave you something, if I said, okay, here's my triangle, and that's a 45-degree angle, and that's 7, and that's x, and that's y, I might say, okay, I need you to find me x and y. Now, the problem with trying to do that with Pythagorean theorem is if we just write 7 plus squared plus x squared equals y squared, I've got 2 missing things. I've got 2 missing things to find. But if you look at it, if this is 45, that means that has to be 45 as well. Why? What do we know about all 3 angles in a triangle? They add up to 180, right? So if you have a 90 and a 45, which is 135, you need 45 more. So you automatically know when that's given 45 that you can fill that in. So what's that mean about x? X has to be 7. Because if your angles are the same size in the triangle, your sides have to be the same. And so 45, 45, 90, if x is 7, what's y? 7 times the square root of 2. Yeah. That's how I'm going to ask you that. This guy's stuff out of the way. We'll go back in. That's our 45, 45, 90 triangle. The other one's a little trickier. But still not too bad. Special triangle number 2. Okay, special triangle number 2. Actually, sorry. Make sure I draw this right. I don't want to draw it to look something like this. It's when we've got a 90 here and a 30 and a 60. Not the most creative name for this either. We just call this the 30, 60, 90. right triangle. At least the isosceles one kind of has its own like fun name, but this we just kind of call it 30, 60, 90 triangle. We have a short leg, and we have a long leg, and we have a hypotenuse. And it does fit the Pythagorean theorem, but there's a second relationship that happens in the 30, 60, 90. And it's not exactly what you would think. Just because 60 is double of 30, the leg is not double the other leg. That's not the relationship. That's not how the size of angles and the lengths of sides in triangles work. If it did work that way, we wouldn't actually have trig as a whole subject. That's one of the reasons we have trig, is because of how to try to relate the different sizes of the angles compared to the lengths of the sides so that you still have a right triangle. When this angle gets smaller, this side gets smaller, this angle gets bigger, this side gets bigger, but there's a relationship that has to stay kind of balanced to make this thing be, in fact, a triangle. I'm going to draw this again. My triangle's just kind of messy, so don't worry about it. You guys, this is fine. So, 30 up here, 60 down here, 90 here. I'm going to show you what the relationship is. And here's what it looks like. If the side across the 30 is whatever number, x, let's call it x, then the side across from the 90 is 2 times as big. Now I know you're like, but 90 isn't 2 times as big as 30. I know that. That's not how angles and sides in a triangle work. They're not proportional in that way. If we double the angle, it doesn't double the length of the side. It does more than that. Okay. 30x across from 90, 2x. Anybody remember this? See this ever before? Mason, you remember this one? Do you remember what the 60 side is? It's got the x and a root 3. Yeah? Now that I wrote that, anybody? Somewhere you're like, yeah, man, okay. This is the 30, 60, 90 relationship. In the interest of time, I'm going to hold off sort of proving this one to you, showing you where it comes from. It comes from the idea of an equilateral triangle. So there's a reason you can kind of, it's a little easier to show the isosceles one. This one takes a little bit more work. But this is the set of relationships in a 30, 60, 90 triangle that we have to be able to look for. If we have this set of relationships, or if we have a 30, 60, 90 triangle, we know we can take one piece of information, any one of these three, and find the other two. Okay. So, how would you be faced with this? I would draw the triangle. And you have to also be careful about paying attention to where the angles are. The 30 at the top and the 60 at the bottom, they can be flipped around. I'm going to go ahead and just do it the same way. So if that's the 30 and that's the 60, and maybe I put a 10 right there, and our job says, okay, I want you to find me the other two sides. First thing you're going to be like, well, there's not enough stuff. I can't do Pythagorean theorem. You're right. You can't do straight Pythagorean theorem because you have two missing things. But you do have a 30, 60, 90 relationship. So when I think about a 30, 60, 90 relationship, I always start, okay, this is the 90 side. So I fill in, you know, what side is that? The 90 side is the 2x side, which means the 30 side is going to be my x side. The 60 side is my x square root of 3 side. And once I fill in the relationship, I go with, okay, I have one equation. The 2x side is 10. So that means that the x side is 5. And if x is 5, then my other leg has to be 5 times the square root of 3. So this has to be 5, and then that automatically becomes 5 to the square root of 3. So let's look at that in a couple different triangles. Let's practice that. All right, so here's my first one. Here. Here's my second one. Sure. There we go. And here's my third one. I know, I'm like the worst at drawing triangles. They're so bad. Oh my gosh, they're so bad. You'd think I could draw a triangle. I think because I'm trying to draw them too small. So 30 there, 60 there, and we'll put here. Okay. Use the pattern for that kind of triangle to find the missing side. We can only use these shortcut patterns for 45, 45, 90, and 30, 60, 90 right triangles. Any other kind of right triangle, we need Pythagorean theorem, and so we may not be able to solve a problem like this where all you have is one side. Well, that's not true. You could do it. You just need trig. Put that 18 in the row. Okay. Let me see what's over here while you guys are doing that. Do, 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 do. What's that mean? I don't know what that means. Okay. Sure, I did that. Okay. All right. So I see a 30, 60, 90. I always go to the 90 first because he's the easiest to find. So he's 2x. The 30 side is x. The 60 side is x root 3. There's the one I know. So that means my hypotenuse side is 8. And my 60 side, 4 root 3. Yeah? No? Sort of? You okay? How are we doing? I see some nodding. Okay. 40, 45, 45, 90. I can do the same thing. My 90 side is the x root 2 side. So the other two sides are x's. So if x root 2 is 9 root 2, if x root 2 equals 9 root 2, that means x has to be 9. So this side is 9 and this side is 9. You can actually do that one with the Pythagorean theorem. You don't have to know the shortcut. Eventually you'll get that the sides are 9 if you, let me just show this for a second. If you had this, and you know that this is the truth, you'd have to know that these two things are the same though. But you could do x squared plus x squared equals 9 square root of 2 all squared. So that would make this side 2x squared. And then this side, if you have 9 square root of 2 times 9 square root of 2, it's going to be 81 times 2, or 162. Oops, let me do it that way. So 9 square root of 2, quantity squared. 9 times the square root of 2 times another 9 times another square root of 2 makes an 81 for the 9s and a 2 for the 2 root 2s. So x squared would equal 81 when you divide both sides by 2, which would mean x would have to be 9. So the isosceles ones, you can get away with not knowing the shortcut, but why would you not want to know the shortcut? Because it's so super fun and easy to do it with the shortcut, and so annoying to do it without the shortcut. If that's 9 root 2, then those bad boys are 9, because they're the same when, and they relate to the hypotenuse in that 45, 45, 9. 18 across from the 90, he's my 2x side. So my 30 side will be 9. If 18 is 2x, that means the x side is 9. And so the x root 3 side is 9 root 3. Ooh, okay. Take a look at this real quick before we go any further. All right. Oh, we're in good shape. All right. Now, in a normal, like I said, in a normal year, we might be able to do that a little bit more quickly. I'm kind of going a little slow, and if you're like, oh, yawn slow, I'm sorry about that. Just want to make sure we're not kind of leaving anybody, no man left behind. Want to make sure we're all following along, because there's no coincidence in the fact that 30 and 60 and 45 are all these like super special triangles, and 30 and 60 and 45 are these like super special angle families. Yeah, it's all going to come together. So we've got to make sure we've got these special angle triangles in our minds when we come back to working with how our unit circle is going to help us do some other things. All right. So, just in case you missed this, this stuff is not on your quiz. You still have time to process this information before I'm going to expect you to do something like this on a quiz or a test. The quiz that we're having in 2 weeks is everything we've done before today. But that doesn't mean we're not going to practice this, because, you know, we're going to need it. Last thing for today. Okay? Last thing for today. When we look at a right triangle, we can create certain ratios, certain comparisons between sides that we call our trig ratios, or our trigonometric ratios. The 3 that you have learned about in the past are the sine and the cosine and the tangent. Now, this is one of the last times I'm going to write those out completely, because you should have seen in the past, if we're talking about sine, we use an abbreviation, SIN, okay, but we still say sine, and COS for cosine, and TAN for tangent. So let's take a triangle. Let's say I have a nice 30, 60, 90 triangle, and let's say that, you know, the 30 side is 5. What would my hypotenuse side be? If the 30 side is 5, what would the hypotenuse side be? 10. Good. And what would the 60 side be? 5 root 3. Yep. No, you're fine. Just do that, and then you can see everything nicer. Okay. So we've got these abbreviations, sine and cosine and tangents, for these 3 functions, or these 3 relationships, or 3 ratios between sides in a right triangle. I'm going to use this 30, 60, 90 triangle to review with you how we create each of these ratios. When I'm doing a sine, I take the length of the opposite side, the sine of whatever angle, the length of the side opposite the angle over the hypotenuse value. So in this particular triangle, if I'm looking at the 30-degree angle, the sine ratio for the 30-degree angle would be the 5 over the 10, which we can simplify to 1. If I was doing from the perspective of the 60-degree angle. And that's what's important here, and this is where I'm going to get up again and kind of do my pointing, right? If we're going opposite over hypotenuse relative to a particular angle, if I'm in the 30-degree angle, here's my opposite over hypotenuse. Hypotenuse is always the hypotenuse. He doesn't change. If I'm in the 60-degree angle, if I'm up here, this leg is my opposite. So opposite is relative to the angle you're in, or the angle you're looking at. So that's, like I said, that's my kind of my go-to is like if I'm in this angle, that's opposite of me. That's opposite for 30 degrees. 60 degrees, if I'm in the 60-degree angle, that side is opposite. It's the one that's not next door to you. And so what am I going to write for, I'm trying to make this as small as I can. What am I going to write for sine of 60 degrees? Very good. 5 root 3 over 10. And that actually simplifies down to 1 root 3 over 2, which we will just leave to root 3 over 2. How many of you remember sine opposite over hypotenuse? And usually the device we use, SOHCAHTOA, or some old horse came a hopping through our alley, or there's another one with the word hooker in it that I'm not going to say. There's all kinds of tricks. There's 3 ratios that we learn. Like, wait, she just said something weird. What'd she just say? There are 3 ratios that we learn first: sine and cosine and tangent. Okay. And when we learn those, we usually learn all 3 of them together, kind of in a row, and we do that our sine is the opposite over the hypotenuse, and that the cosine, we use the word adjacent. So basically the side that's not opposite is the adjacent over hypotenuse. Now the important thing is hypotenuse doesn't change, right? So you have to know who the hypotenuse is because that's fixed. And then, do you remember what tangent was? It's SOHCAHTOA. What does that make tangent? Opposite over adjacent. Opposite. Now, if you're sitting there going, well, how do you do like sine of 90? You can't with a triangle. You can do it later. There's a way to do it, but you can't do it with a triangle. So it's, because the 90-degree angle has sort of, its opposite is the hypotenuse. Which, so doing the sine and cosine and tangent ratios like this with a triangle, these are only things you can do with the non-90-degree angle. It doesn't have to be a special right triangle for us to write sine and cosine and tangent ratios. If we go all the way back to one of our other triangles we figured out, okay, like our 2, 3, root 13 triangle. Oops. This is when I get in trouble, when I start jumping around. Jump around, jump around. Okay, so there we go. I'm gonna add more. All right. So I have this, oops. What did I do with that page? Oh, here he is. Okay. Yeah. So a big part of this, I hear you guys talking, a big part of this is kind of visualizing who's what, who's opposite and adjacent. So let's talk about this guy. If we do that 2, 3, root 13 triangle, maybe. And let's talk about this angle. We'll call that angle W for Willenbrock because that's awesome. If I was going to write the sine of W, what would I write? Two over root 13, yeah. And then the cosine of W would be 3 over root 13. And then the tangent of W would be 2 over 3. Because if this is my focus angle, that's opposite. This guy is automatically hypotenuse because he's across from 90, so he ends up having to be adjacent. All right, I have another assignment for you. You're like, yay! You should be able to do the front. You should be able to do part of the back. There are some ratios on the back that we didn't introduce yet. We will get to those. So on this worksheet, I want you to do the entire front and then see what you can do on the back. By class on Wednesday. And before you leave, do not forget to turn in your other homework packet. To the basket, yep. That's always the best place to put it. Okay. So I'm going to write this on our video. Hi, come on in. Thank you. Alexis, Charisma, presentes for you. Thank you, sir. I like your purple pants. So we're turning in the packet, and we're going to remember that. I'm going to write down, and I will post the video, and I'll write down the video. So homework. There's a new homework worksheet. Whole front. And do what you can on the back. And you're going to have your computer all ready.